Okay, at this point, what we need to do is to become comfortable with proving statements of the type, this sequence converges to a certain number. And for that, most of the examples that we asking you to show by definition, that the convergence by definition will involve some rational expressions, meaning that you have a polynomial over a polynomial in n. Of course, there are other more complicated examples, but as long as you understand the basic principles behind these more elementary things involving only rational functions, everything else should just follow as a generalization. And if you have any trouble, you can encounter any troubles generalizing this to other examples, just let me know and I'll be happy to answer your questions. But so once I wanted to start with an example. I think the best thing, because this is something I'm definitely going to ask you to do for the second midterm. So let's look at it this way. So consider the sequence consider the sequence n squared plus 3, no, oh, it's just a sub n, I'm sorry, a sub n is equal to n squared plus 4n plus 2, say, and divided by 3n squared plus 5n. This is something that you must have seen in Calc 1. In case you don't remember, just pick up any calculus book and you have expressions like this. It's perhaps not with n, but with x. So I'm asking you to show here. So as n goes to infinity, a sub n converges to what? Does it converge? So first of all, so as n goes to infinity, does a sub n converge? That means that a sub n is going to a certain number. Has a limit L or A, and the way we defined in the previous video. So meaning that for every epsilon there is an n such that blah blah blah. And if there's no such number, then a n is said to be divergent. So does a sub n converge? So to begin with, can we actually say that a sub n converges? Remember, we're using this for the sequence defined. So the sequence defined by this. If yes, what is its limit, and prove it, and prove that this is indeed the limit. So, and the reason why I wanted to draw your attention to this is the fact that, first of all, what you need to do is to identify a potential limit. So a candidate for the limit. For the limit for A. Of the sequence. And at this point, you can simply operate at a formal level. You don't have to show anything. The proof comes after. You make a claim once you've found the candidate for the limit of this expression of this for this sequence, and then you're left with the task of actually showing that that is the limit. So what is the limit? Then if you remember from Calc 1, you were probably used to doing something like this. Sorry, it is 3n squared plus 5n. So you were used to taking out a factor of n squared on the top and the bottom. 4 over n plus 2 over n squared divided by n squared times 3 plus 5 over n. And you cancel out the n squares and you say this goes to 0 because n is becoming very large, and for the same reason 2 over n squared. 5 over n is also becoming very small because n is very large. So this should be going to 1 over 3. So this implies that A equals 1/3. Is the only candidate for a limit. Of the sequence. And so now that we have a candidate, well, again, piece of warning here, this is not a proof. This is a formal argument. This is just a at this point, at this level, this is just a formal argument. This is not a proof that a sub n converges to 1/3 as n goes to infinity. It's not a proof that it converges at all. It's not a proof that it converges to 1/3 specifically. To much less that. I mean, that is a specific limit. This is just some back of the envelope computations that you do in order to identify a candidate, which should be your first step. Identify a candidate. Now, to actually prove this is indeed the limit, we go back to the definition. You need to go back to the definition because that's what we're trying to show. That is the property that we were asked to prove. That for every epsilon there exists an n such that for any value of n greater than that capital N, a sub n minus a, in this case 1/3, in absolute value is less than epsilon. So this is what we need to do. So first, the first thing, let epsilon be greater than 0. Be an arbitrary small number. I mean, just a given number. Epsilon is greater than 0. And so now the task is to find n. So we need to find n in terms of epsilon that will make the rest of the statement true. This is perhaps a minor thing, but I'm separating it as a first step because many of you forget that, I mean, the quantifiers, and here we are supposed to do this for every epsilon. So the first step consists of taking one epsilon, I mean, just picking any arbitrary epsilon and sticking with it for the rest of the argument. Okay, so here we're not doing actually anything. I'm just trying to draw your attention to the fact that there's an epsilon that you need to fix at the beginning. Second step is you need to try to find n, the capital N. And so what you want to do is to make sure that, so what is the limit here? 1/3. You want to make this smaller than than epsilon for values of n greater than a capital N. So you write down what this is. So if you remember, this was equal to n squared plus 4n plus 2 divided by 3n squared plus 5n, and then minus 1/3. Okay, so yeah, so n squared plus 4n plus 2 divided by 3n squared plus 5n. Then we can write this as a single fraction, and we get here that we have 3n squared plus 4 plus 12n plus 6 minus 3n squared minus 5n. All of that divided by 3 times 3n squared plus 5n. Not surprisingly, 3n squares here will cancel out, so you have that this is going to be equal to 12 minus 5n is 7n, so 7n plus 6, all of that divided by 3n squared plus 5n. In absolute value. And we want this to be smaller than epsilon, remember? So we're going to bound this some quantity from above. And remember that we need to find an n that is large enough. So we can allow ourselves to take values of n that are big enough so that certain statements here are going to be true. So first of all, when you're dealing with expressions like this, you want to get a string of inequalities here at the end of which there will be an epsilon. So if you impose that this quantity here at the end is less than epsilon, then you will be able to say then this quantity was going to be, it's going to be less than epsilon, because you have a string of inequalities. So what you want is to bound this expression from above, this quotient, and you achieve this by making the numerator bigger and the numerator bigger and the denominator smaller. And so we're gonna keep track of every assumption that we make along the way. So for instance, 6 is a fixed number, so after a certain point this is gonna be less than n, particularly when n is greater than 6. And what we're doing here, this is going to be less than 7n plus n. I'm just writing everything, just not to keep track of whatever we're going to be saying here. So 7n plus n. All of that divided by 3, well, we can take the 3 outside of the absolute value. And this is going to be true, this inequality, when n is greater than or equal to 6. No, greater than 6, because we're using just strict inequality here. This is going to be true when n is greater than 6, because this term here is going to be greater than that. It's going to be larger than that. And so now we've simplified it. The whole point here that I'm trying to make is that we have to simplify this expression to be able to find a value for n. Before, in the previous example, we just had 1 over square root n in smaller than epsilon, so you just turn this into a statement about saying that n has to be greater than 1 over epsilon squared, because you can solve for n. Here, solving for n will be very impractical, and it will be virtually impossible if we use polynomials of say degree 5. So it's you're gonna have to bound at some point anyway your expressions at some point. So you might as well do it from the beginning. Since you only care about the existence of one n, you don't want to find the optimal n. You just want to find one n beyond which this quantity that we have at hand is smaller than epsilon. So this is equal to 8n. So on the top we just get 8n. I mean, n is a natural number. It is positive. Okay, so it's definitely non-negative. So the absolute value of that of 8n is just 8n. And we divide this by 3 times 3n squared plus 5n. So the goal here, as I said, the goal here is to make to write down an explicit expression, a very simple expression that will allow us to solve for n. Here this is still too complicated. We'll simplify, so we want to have just one term for the numerator and one term for the denominator. We've accomplished this for the numerator, so we just replace everything by 8n. And we need to do the same thing for the denominator. But the way we do that, we make this larger, is by making the denominator smaller. Of course, you know the n squared eventually beats n, and we could just replace 3n squared by 3n, but then we would be left with something that doesn't depend on n. Try that and see what I'm trying to say. So if you do that, you'll end up with 8n over 3 times say 8n, and that would just be 1 over 3. Right, so there's no way you can make 1 over 3 smaller than epsilon for a certain value of n. That expression doesn't even depend on n. So we have to be, so that expression doesn't depend on n. So we can never find a value of n that would make 1/3 less than epsilon for every epsilon, because just pick 1/6, and that's going to be smaller than that. So there's no way to do that. 1/3 is just 1/3. So we need to be smarter about it. So we want to bound this from below by something that is 2 quadratic. So 3n squared plus 5n. Remember, everything here is positive. So this is definitely greater than 3n squared. Because here you're adding 5n to that. Right? So if this is greater than that, I mean, remember we want to make the denominator smaller. So we're going to replace this by 8n over 3 times 3n squared. Yeah, so value still. And this is valid actually for all n. So we're just asking that this is that n is greater than or equal to 0. Nothing more than that. Finally, what's in the denominator is equal to 3 times 3 times n squared. Everything involved is a positive number. All the terms here are positive numbers. So you get 8n over 9n squared. And you may cancel the n's here, and you get 8 over 9n. And we want this to be, and this is the final step, this is what I was mentioning before, we want to be this to be less than epsilon. And this will happen, if what? Just solve for solve for n. So what will happen if n is greater than 8 over 9 epsilon. So as long as n is greater than 8 over 9 epsilon, this inequality will be true. And how do we know there's such an n? At least one n? Well, the Archimedean property again. So we choose to be a n, well, we choose n in n to be such that n, that 8 over 9 epsilon is less than n. This is just any n. This is just any n, so this capital N here is just any n that satisfies this property. This is just any n. We're picking just any n, and the thing here is that once we find such an n, that n has to be fixed. Okay, epsilon is fixed, and we found an n, a capital N, and then now we have to test our property for every single n greater than or equal to this n, this capital N. So, but if this is true, and we know this capital N exists again because of the Archimedean property. So now if n is greater than or equal to n, then certainly 8 over 9 epsilon is going to be smaller than n, is going to be smaller than, it's going to be smaller than capital N, which is going to be smaller than n. It's smaller than or equal, less than or equal to n. And so then certainly n is going to be greater than 8 over 9 epsilon is going to be smaller than n. But if that happens, if n is greater than 8 over 9 epsilon, then if you go back here, this expression to the top, what we have is this an minus 1/3 is less than epsilon. So what we've shown, and this implies in turn that an minus 1/3 is smaller than epsilon. So here, I want you to pay attention to what we're doing here. So epsilon is given at the beginning. We haven't changed it at any point. We found an n, a capital N. Now, if n is greater than or equal to n, what can we conclude? That an minus 1/3 is less than epsilon. It's smaller than epsilon. And that is the that is the property that we needed to show. That there was an n, which we found. This was this capital N, which we chose to be any capital N such that any number that was greater than 8/9 epsilon, which exists again because of the Archimedean property. And so for any values of n greater than or equal to that n, we can say for sure that this quantity is going to be less than. We can guarantee that an minus 1/3 in absolute value is going to be less than epsilon. And this is the statement for the limit, what we wanted to do. So this is the goal here in every such problem. Whenever you see any problem like this is what you want to do. And I expect you to do this. I mean, I'm gonna ask you to do this for sure for the exam. Okay, so I want you to follow these steps. I mean, it's once you go over this example again, I mean, it will become clear what you need to do. So first of all, we had to find a sequence. So a sequence of a sub n, so numbers a sub n. In this case, it was just a rational expression, so a polynomial in n divided by another polynomial in n. And the first thing, before even going through the steps, is to identify the limit. And we do this by doing the same kind of thing we did in Calc 1. So just factor the n squareds out and identifying that there's a limit of 1/3 by this formal argument, saying, oh, this goes to 0, this goes to 0, and this goes to 0, so this goes to 1/3. So once you find the candidate for the limit, then you move on to the actual rigorous part. So you want to show that 1/3 in this case is the limit. So you have all the parameters that are needed for you to have in order to show that something is the limit of a given sequence. You need to have a candidate, a number that you're aiming for. You are aiming to show, you want to show that that number, in this case 1/3, is the limit of the sequence. You need to find that number first. It's not given to you. But again, at this stage, this is just a formal computation, nothing more. Next thing is to just go over the actual proof, because you've determined that the missing piece, which is the value of the limit, and you have to show that that value for the limit actually corresponds to the limit, and you have to do that rigorously. So the first step is to take an epsilon greater than 0. Second step is to take an minus the candidate for the limit and do these operations again. Bound what you have in the end by simplifying everything, so you have only one term on the top and one term in the bottom. So you can, but not simplify it so much that you end up with a constant. You just have to end up with something that depends on n. And you achieve that by bounding things from in the numerator from above and the denominator from below. Okay, so you want to make the numerator larger and the denominator smaller. Okay, and then at the end, you are gonna have, you're gonna end up with a restriction for n. N has to be greater than 8 over 9 epsilon. And then that's going to imply that an minus 1/3 is less than epsilon. I forgot here actually something. This is why it's good to go over this argument again. Here we're actually assume two things. So that this was true. So 8 over 9 epsilon was less than n, and that n was greater than 6. So we actually have to pick a number that is greater than both 8 over 9 epsilon and 6. Usually, since you're considering epsilon to be very small, this condition alone will guarantee that you have the property you need at the end when you want to go to the last part of the argument. In fact, this is just the third step. Is to verify that our choice, the choice we're about to make is going to be the right thing to do. Such that not only n is going to be greater than this, so let me correct this. Not only that n is greater than that, but n has to be greater than the maximum between 6 and 8 over 9 epsilon. So whenever you go over these inequalities here, keep track of every inequality that you got for n, because n then has to be greater than all these choices. So it's to be greater than the biggest of these numbers. Of course, as I said, typically you think of epsilon as being really small, so as long as n is greater than this 8 over 9 epsilon, then of course that's certainly going to be greater than 6. But since you have to do this for every epsilon, then you have to be you have to pay a little bit more attention and make sure that your choice is correct. So n greater than that. So now if n is greater than or equal to n, then for sure n is going to be greater than this thing. And then that's going to imply that this is true, provided n is also n is greater than or equal to n, which is greater than 6. Okay, so and that's the case. So remember, this inequality here was true because n was greater than 6. So in reality, I should say, so this is what allows you to conclude that this is true, ultimately. So this is the final thing, and since little n is greater than or equal to n, which is in turn greater than 6. So to conclude this, you needed two things. Remember, we assume, actually, well, three things, but one we have for sure. We just need n is greater than or equal to 0. And n being greater, the other requirement being that n is greater than 8 over 9 epsilon, and the last one that n is greater than 6. Okay, so that's it for the for how you have to proceed when you do this kind of problem. And well, just study the material and go over it again. If you have questions, make sure to ask me, because this is something I'm gonna be asking you to do. So this is something you're gonna have to do, and we're gonna be seeing a lot of this. Not perhaps the same kind of argument, but something very similar in the near future, and for the rest of the semester, for that matter. May not do to you like the same, but it's going to be. And once you get used to this, it becomes easier with more practice. Okay, so good luck, with your study, and that's it for this week.